Okay, so we're backtrack and look at the formulas we had in section 6.4. Two arc length formulas. One was for rectangular coordinates. In which we're looking for how long of an arc is produced. That's cutting me off a little bit. Straighten out the camera a little bit. Let's see, this way some more. Let's try that now. Still not, still not. Hold on, why didn't you do anything? Oh, well, I'll just move over. So in rectangular coordinates, we've got some function y is equal to f of x on the interval from a to b. And we found the arc length s by computing the interval from a to b of the square root of 1 plus f prime of x times dx. For polar coordinates, we have some function r is equal to f of theta, where theta is between a and b. Theta is our independent variable. The arc length formula looks similar but different in that it had an r squared right here. Both of them, though, come from the distance formula. And both of them can be difficult to integrate because of the square root sign. So a lot of your problems in this section are contrived in such a way that we end up with a u/du integral or something under the radical sign that's a perfect square. So remind me how many examples we worked last time. We did 2 examples here, maybe? Did we do one that was a perfect square? We did one? Yeah. Okay, so let me do some examples that are here. Let's just take a circle. Line, length of arc of r is equal to 6 times about sine of theta from theta is equal to pi over 6 to theta is equal to, let's go all the way over to 5 pi over 6. First, let's look at a picture and make sure that that's viable. What kind of picture does this thing have? R is equal to 6 sine theta? Circle up there on the y-axis. What's the diameter of this circle?
6.
6 down to 6. So pi over 6 should be something in here. And 5 pi over 6 should be something in here. And so the arc whose length we are finding is this bit right there. Measuring that. What's the total circumference of this circle? Circumference of a circle is pi times diameter. So the total circumference is 6 pi. So I've cut off a 30-degree arc here and a 30-degree arc there. So I cut off 160 degrees out of 360 is 1/6 of the circle is cut off. So take, what did I say, 6 pi? So I cut off 1 pi. So I'm betting this is going to be 5 pi. So let's look. Let's look at our arc length formula. I need r prime. So here, dr d theta is 6 cosine theta. Now we're going to fill it into this polar form right there. Got our square root sign. Now our r squared plus our derivative of r squared. Then we integrate with respect to theta. And we're going to go around here counterclockwise from pi over 6 to 5 pi over 6. And so we do the squaring, and inside I get 36 sine squared plus 36 cosine squared. Now you cannot take the square root of each term, but you can factor out a 36. And if you factor out a 36 from here, under the radical sign, you'll have the 36 times the sine squared theta plus cosine squared theta. And that should make you happy. What is sine squared theta plus cosine squared theta?
1.
That's just 1. So I get the square root of 36. That's just 6. Integrate the constant with respect to theta. We'll get that constant times theta from pi 6 to 5 pi 6. And so I have 6 times 5 pi over 6 minus 6 times pi over 6. And so I have 5 pi minus pi. And that's 4 pi. Is that what we said we should get? It's not, but then I did bad mental math. Okay. All right, now, if you, for instance, put in here something as similar to this as maybe a 3-petaled rose, then we're going to get an integral that we can't do. If I have a 3-petaled rose, I'd have a 3 right here next to the theta. And so the derivative would have a different coefficient, which means I'm not going to have the 1 in here. I'm going to have, for instance, a 6 sine squared theta and 18 cosine squared theta. And so I wouldn't be able to factor out the sine squared, cosine squared. I got a big old mess, and I already don't know how to do it. Take a cardioid, same deal. We take the cardioid, take its derivative, square it. I'm not going to have anything that we can have an integral that we can compute. So some of the polar functions that you see here in this section are a little bit different than the ones that you're familiar with. For example, this polar function find the arc length. F of theta is equal to e to the 6th theta. Say from theta is equal to 0 to theta is equal to pi over 6. This is a graph where r grows as e to the 6 grows, which grows real fast, right? As theta increases, the power increases, e to that power gets bigger, and as I move around the unit circle, r just gets big real fast. It generates a spiral. Over this small interval, it just might be a part of the spiral, but typically this graph would look something like some sort of spiral. We're only getting one small part of it, from 0 to pi over 6. Okay? But I chose this because this is another example of a function whose derivative, in this case, is itself, and I'll be able to combine terms in here after I square them. Okay, so let's apply the formula to this thing. Let me rub off some of this stuff and apply the formula. So our formula, we need an r and a drd theta. So in this case, drd theta is the derivative of e to the 6 theta. So you get itself times the derivative of the exponent. So I get an extra factor of 6 right there. Now we plug it into the formula. S is equal to the integral of the square root of r squared plus the derivative of r squared. So in this case, we're integrating from 0 to 6 pi. Sorry, pi over 6. R squared is going to be e to the 6 theta squared. Drd theta is going to be 6 e to the 6 theta squared. And that's under the radical sign. So help me out here. How do you raise a power to a power? Multiply exponent. So e to the 6 theta squared is e to the 12 theta. But here I'll have to square the 6 as well. And we get e to the 12 theta plus 36 e to the 12 theta d theta. So I get like terms, which means I can add them and get a total of 37 e to the 12 theta in there. And I've got product. You can take the square root of each term in a product. So I'm going to take the square root of 37 and put it out front. What do you do when you take the square root of e to the 12 theta?
E to the 6 theta.
E to the 6 theta. The square root is a 1/2 power. When you raise a power to a power, you multiply exponents. So this is going to give me the square root of 37 times the integral of e to the 6 theta. Quick, what's the integral of e to the 6 theta?
1 over 6 times e to the 6 theta.
1 over 6 times e to the 6 theta is right. So here's the 1 over 6. Whoops. Then here's the e to the 6 theta. And we have to evaluate that from 0 to pi over 6. So when I put the pi over 6 in there, I get e to the pi. When I put the 0 in there, I get e to the 0, but that's 1. So here's our arc length, whatever goofy number that is. Okay? You see any more examples, either in rectangular coordinates or in polar coordinates?
Functions, this kind of stuff.
Define weird polar function.
I mean, stuff that we can't.
Or you could set up the integral, right? That's about as far as, right? Let's just take the cardioid and set up the integral and point out why we don't know how to finish it. Let's take the cardioid. So set up the integral for the arc length of the entire cardioid R is equal to 1 minus cosine theta. And let's look at it, because we need to look at where it is so that we can pick the limits on our integral sign. With theta is 0, cosine of 0 is 1. So if theta is equal to 0, R is 0. If theta is pi over 2 or 3 pi over 2, the cosine is 0, so R is going to be equal to 1. And when theta is pi, cosine is a negative 1, so R is going to be 2. So here's our cardioid. That means we can integrate from 0 to 2 pi to get the whole thing. Or if you want to double it, you can integrate from 0 to pi and double it. Doesn't really matter because there's not that one factor of half-half here. The formula requires the derivative. The derivative is real easy to do. The derivative is what? Minus sine of theta?
This case it'd be sine, right?
Sorry?
Would it just be sine? Because there's a
Oh, because
negative.
you're in cosine's a minus. We're allowed to make mistakes like signs on Fridays, aren't I? So it's positive sign. Anyway, in the integral, we've got to square those, add them together, take the square root, and then integrate. So let's see how far we need to go before we decide we don't know how to integrate this. So we're going to have 1 minus the cosine of theta squared plus the sine of theta squared d theta. So that's 1 minus the cosine all squared. That's not our Pythagorean identity. That's a binomial square. When you square it, you get 1 minus 2 cosine theta plus cosine squared of theta. And then you get a sine squared of theta out here. I said we can integrate from 0 to 2 pi, get the whole thing. You can replace the cosine squared plus sine squared with 1. Then our integrand will have a 2 minus 2 cosine theta underneath it. Then what? It's not a u du integral because my du doesn't have a, my integral doesn't have a sign out here. I can't take the square root of each term with a difference. We don't know how to integrate this. I'm mentally going through all of my trig identities. Not coming up with much, but that might have something to do with it being Friday. So there's nothing we can do. We're stuck right here. We don't know how to integrate this. Okay? We don't know. I don't even know how to spell. I don't know how to do this. Right, it's a definite integral. We could probably go plug it into Mathematica and have it do it numerically for us. But in terms of our integration skills, that's where we'd have to stop. So, like I said, all the problems in this section in which you need to carry out the integration are contrived in such a way that you'll either have a UDU integral or something that you can write as a single term and then take the square root of it. So just be on the lookout for that. Make you think of anything you want to ask? Okay, then let's jump to 6.5. We're compiling all of our applications of the integral in this chapter. We started with integration to compute areas, then integration to compute some volumes. Then we moved over to polar coordinates so that you had more functions to integrate. Then in section 6.4, we're looking at arc length. 6.5 has actually 3 more applications. One of them will be applied to work. Another one will be fluid force. And another one will be finding the center of mass. So I'm going to kind of break up this section into those 3 parts. So you guys are engineers or physics people or something like that? How is work defined in engineering and physics?
Application of force.
Application of force that does what?
Or
Moves an
actually
object.
changes the net force. If it's already moving, it work like this, like the net force goes positive.
Okay, but in general, you have to apply a force to something and it's got to be displaced. Then work is done. So even if I get up here with all of my massive strength and push against this wall as hard as I could till it pop a few veins and that wall doesn't move, then I've done no work. Work is an application of a force on an object that displaces the object a certain distance. For the first part, we're going to talk about work. Work refers to a force on an object and the object is displaced a certain distance. And so if your force is a constant, then work is just that constant force multiplied with the distance. For example, if I pick up a 20-pound bag of potatoes and put it up here on this table that's about 4 feet high, I've done 20 pounds times 4 feet of work. Or I've done 80 foot-pounds of work. Feet. But if I have a bucket of water that weighs 20 pounds, but this bucket has a hole in it, so it leaks water as I lift it. And so here it might be 20 pounds, here it might be 18 pounds, here it might be 16 pounds. As I lift it, it gets less and less in weight, then my force is not constant. My force varies on a number line. So if the force is going to vary along the number line, here's what we do. What's what we do in calculus? We take our interval and we cut it up into teeny tiny intervals so that that force on a teeny tiny interval is roughly a constant. And we multiply that roughly a constant force times the length of that teeny tiny interval. And we do that for each interval and add them up with an infinite sum. And then we let the number of intervals go to 0, and out pops an interval. If force is not constant, suppose we're moving an object along a number line from x is equal to a to x is equal to b, and the force acting on the object depends on where it is on the x-axis. And suppose the force acting on the object is just a function of x, capital F of x. So the force depends on the location of the object on the x-axis. Then we subdivide the interval from A to B into many subintervals so that on each subinterval, the force is essentially constant. So here's the kth subinterval. My object is somewhere between xk and xk plus 1. The force acting on that object is roughly constant. Let's say it takes on the value of some intermediate point xk star. And then the force on this one subinterval, the work on this one subinterval is roughly that. The work on the kth subinterval is roughly just the product of whatever the typical force is over that interval times the length of the interval. Then we make the Riemann sum. Gives the total work. We take the sum from k is equal to 1 to n of products of that nature. We let n go to infinity, which in turn makes our intervals go down to a single point. And this work becomes a definite integral from a to b with f of x here and dx there. And so in most of this section, we're going to spend our time figuring out what the integrand is. Sometimes it'll be given to us, but most of the time we're going to figure out what it is. Let's see if I had any problems on that handout for you that sent this stuff. Oh, there it is. There it is. So I sent in your email a handout of examples so that we all wouldn't have to write things down. Did you print you one or get you one, or am I writing all these problems down? In my first example, I've got a cable 50 meters long, and the density of this cable is 3 kilograms per meter. And we're going to wind that cable up. So here all of a sudden I've gone away from my feet and my pounds. So I need to maybe take a time out here and talk about units of work before I start. So we've got our the system of units in the United States, US units. Force is in pounds, distance is in feet, and so work is in foot-pounds. That to me makes a lot of sense. But in the metric system, we've got distance in meters. What's the force usually in a metric system?
kilogram.
Kilogram meters has a name, doesn't it?
Yeah.
Newtons. Kilogram meters are newtons.
No, Newton is force, kilogram is mass.
Right. I'm gonna point that out too. And so a Newton meter is called a joule. When we have smaller measurements, like we're going to talk about the work done in stretching or compressing a spring, and things are measured in centimeters, and then the force is measured in dynes, we get my all-time favorite unit of work, an erg. It even sounds like you're doing work. Erg. Wouldn't you like to be there when that name was made up? It was called ergs. But anyway, in the United States system, when we talk about force, we talk about, that comes true when we talk about water. Let's just worry about this for now, and I'll mix that in later. But a lot of your web work problems require units, so you can always look them up, I suppose. But let's look at that chain problem. If this chain has a density of 3 kilograms per meter, well, then I can figure out its weight density when it's all dangling there. But as it's being rolled up, just like the leaking bucket, the weight density changes. So the amount of force is going to vary depending on how much cable is left dangling there. So what I'm going to do for number 1 is what I did here. I'm going to dangle my cable right here in front of you, and then I'm going to cut it up into little slices. And I'm going to figure out the work done in moving a small slice and put that in an interval. So I'm going to make this y-axis here to help me measure the cable. I've got the cable 50 meters long, so let me denote that as the cable, even though that looks like a string. All right, there's my cable. And it's 50 meters long, so this is the ordered pair 0, 50. Here's the origin. And I know it's 3 kilograms per meter. And we want to find the work done in winding it all the way up. So I've got a couple of things I need to do. I need to cut this cable into a little tiny piece. Let's go out here somewhere on the y-axis and make a piece of length delta y. Delta y meters of chain. In that delta y meters of chain, at 3 kilograms per meter, then the force needed to move just that one little slice is 3 kilograms times delta y. 3 kilograms per meter times delta y meters. The meters will cancel and gives us 3 delta y as our unit of force in kilograms. Now I need to see how far that little slice of chain has to move to get to where it's wound up. So I put it at some arbitrary y coordinate, and I need to get it from this arbitrary y coordinate all the way up to that y coordinate. So what is the distance that that slice has to move?
50 minus
50 minus y. And so the distance, the slice is displaced, is 50 minus y. Now we've got a Riemann sum, adding all of those up. We take the limit, that part, that product of force and distance goes in our integrand. And so our integrand will look like the integral of my 3 delta y. Well, the delta y becomes the dy in our integral sign. And then our distance is the 50 minus y. One more set of hands. So my Riemann sum, like I said, for those forces times the distance, or those are subscripted y's, right? So that's what the way Riemann sum looks like. And so my integral becomes 3 times 50 minus y. The delta y becomes the dy. And then I have to integrate this over all possible places to slice up my chain. And so I can go anywhere from y is 0 to y is 50. And that should give me the work. So the integral is easy to finish. I can take out the 3, integrate 50 minus y, and get 50y minus y squared over 2. When I put 50 in there, I get 2,500 minus 2,500 halves. And so I get 2,500 halves, multiply that by 3, and we have 7,500 halves. 25 times 3 is 75. My units here would be, what was my force? Kilograms times meters, which we said was our joules. Okay. The next easiest type of work integral to compute is work done in stretching or compressing a spring. Because there's this dude named Hooke that tells us what the force is. Any of you know Hooke's law? Every spring has some sort of natural length where it just sits there. Hooke's law says that the amount of force required to displace a string from its natural length to x units beyond natural length is directly proportional to that number x. In other words, the force is a constant times x. You can also compress a spring. So every spring has a natural length. Then you have to apply a force to it to stretch it out a bit. So suppose we stretched it out from its natural length to x units beyond natural length. Hooke's law states that the force required to do this, force required to stretch a spring to x units beyond its natural length is directly proportional to that number x. In other words, it says force is a constant times X. Each spring has its own spring constant. So you'll have to have some information about that spring to determine the spring constant. Then if you're interested in the work done in stretching the spring a certain distance beyond its natural length, you've got your integral, force times the distance, f of x dx. The numbers that go on the integral sign represent the distance beyond its natural length. So if we're going from natural length to a certain distance, we would integrate, say, from 0 to whatever that number is. If we've already got it stretched out a certain distance beyond its natural length, and we want to go from there to there, then we'd integrate from A to B. So we're going to assign 0 to natural length and then increment up from natural length. Okay, so the numbers on the integral sign are measured from natural length. So natural length corresponds to x is 0. Yes.
Hey, on problem one, why isn't gravitational acceleration?
Because I'm assuming that it's in here. So I'm simplifying the problem. Right? Most of the time when you're dealing with metric units, you get to stick in the old force of gravity. So I'm assuming that it's already stuck in here. When I told you about the weight density. So the weight density is going to be different than mass density. The weight density will have the gravitational constant already factored in. The mass density will have to be multiplied by the gravitational constant. What's the gravitational constant in metric units? 9.8. So I think we got time to do one of these. Number 2A on this handout says that a force of 3 pounds is required to hold a spring stretched 1 foot from its natural length. Now we want to find the work done in stretching the spring a total of 6 inches beyond its natural length. So we're told the force is 3 pounds to stretch spring 1/4 of a foot from natural length. And we're asked to find the work done in stretching the spring 6 inches beyond its natural length. So the important thing is to know what you have and know what you're looking for. I've given you an ordered pair, F is 3, X is 1/4, that satisfies this equation. That'll help me determine the spring constant. Once I have the spring constant, I'm then asked to find work. And work is going to be the integral. So first, use this to find the spring constant. We have F is K times X. So my force was 3 pounds. My X was 1/4 of a foot. It's distance beyond the natural length. So if I solve that for K, I get K is 12. Now that I know K, I can set up my integral to compute work. Work is 12x dx. Sorry? That's right. We've got to make sure our units agree. We've got to put everything back in terms of feet. Foot pounds would be our units of work here. So that's a half a foot. And we're going from natural length to this half a foot. So we integrate from 0 to 1/2. So we integrate, get 6x squared, put in the 1/2, and you get a fourth. So you have 6/4 foot-pounds. And now I put in a part B to see if you can catch the difference in the two problems. See if you can see the difference in the wording. So quickly read through part B here. This time a spring has a natural length of 14 centimeters. You're told it takes 50 ergs of work to stretch the spring from this 14 centimeters to 16 centimeters. So now I want to know how much work is it to take it from its 16 centimeters to 17 centimeters. Everything talked about in this particular example is work. It takes work to do this, find the work to do that. Catch that? Okay, so let's take that first sentence and write the integral that the first sentence is telling us. So you have 14 centimeters. You're going to stretch it 2 more centimeters. And it takes 50 ergs of work to do that. So state for me the integral that says that.
You go from 14 to 16,
So 50 is equal to the integral.
from 14 to 16.
I don't want to go from 14 to 16. I'm going to say 14
Oh.
centimeters corresponds to 0. And then 16 centimeters corresponds to 2. I don't know the spring constant yet, but this is the equation that we solved to get the spring constant. So bear with me. We integrate this. We get x squared over 2 from 0 to 2. So we get 4 halves, which says 50 is 2k. That means k is 25. So now when we set up the next work integral, we know what the k is. So next, okay, so now we're at 16 centimeters. And we want to know the amount of work done to take it 1 centimeter more. I don't want to worry about the work to get me to here. I just want this work done over this 1 centimeter length interval. And so my integral is going to have that 25 where the k is. And you're going to tell me what numbers go on the integral sign.
2 to 3.
It's already at 16, and then it's going to go to 17. So 2 to 3. 2 centimeters beyond its natural length to 3 centimeters beyond its natural length. Okay? And then blah, blah, blah. Okay, so we'll pick it up in computing work done on pumping tanks from water. It'll be easy on Monday as well. So bring your little thinking caps and bring a handout so that I don't have to write all these out in full detail. Yes, sir.
For the compression, do we still define like the natural at 0? Because wouldn't
Yes.
the top be negative stuff?
You could have a negative, but then you'll just have to interpret your negative rates.
Okay.
Or you can just turn your axis around and make it.
Oh, say like it's stretching it. Okay.
So it's up to you. Just however you set your axis, then you can interpret your answer.
That makes sense.
Good. Anybody at home have any questions you want to ask?
No, I don't have any. Thank you so much for class today.
All right, thank you. Good job.
Oh,
Yeah.